Chapter 8, Module 3. With the machinery developed in the previous modules, we are now going to introduce the homology groups, the simplicial homology groups of a simplicial complex. For that, we need to define certain concepts. We start with defining chain groups, then boundary homomorphisms and chain complex. Throughout our discussion, we use the following notations and conventions. We deal with only finite simplicial complexes. So, for each dimension q, there are at most finitely many q simplexes in K. SQ will denote the collection of all q simplexes of K, where q is any integer between 0 and the dimension of K. Now, each q simplex sigma q can be equipped with two possible orientations. One is positive sigma q and the other one is negative sigma q. Considering plus sigma q and minus sigma q as two different objects, the collection of all oriented q simplexes is denoted by SQ tilde. So, the number of elements in SQ tilde is twice the number of elements in SQ when q is not equal to 0. And if we take the set S0 as the collection of all 0 simplexes and S0 tilde as the set of all oriented q simplexes, then we know that a 0 simplex is always positively oriented by convention, and therefore, the number of elements in S0 and S0 tilde are same. Now, we define what we call a q chain. Suppose K is a finite simplicial complex and q is an integer between 0 and dimension of K. For any q strictly greater than 0, a map f from SQ tilde to Z is called a q chain if f of minus sigma q is equal to minus of f sigma q for each sigma q belonging to SQ tilde. Any map f from S0 tilde to Z is called a 0 chain. Now, the collection of all q chains is denoted by the set CQK for 0 less than equal to q less than equal to dimension of K. And since CQK consists of certain z valued functions, we define addition on this set CQK in usual way. That is, for all sigma q belonging to SQ tilde, we define f plus g of sigma q as f sigma q plus g sigma q. Since the range of f and g are integers, f sigma q plus g sigma q gives us an integer. Now, it is easy to see that this collection CQK with respect to the addition so defined is an abelian group for every q lying between 0 and dimension of K. So, we have the definition of q dimensional chain group as follows, that a group CQK with respect to the addition defined above is called a q dimensional chain group of K for every q between 0 and dimension of K. It is customary to define the chain groups as trivial groups for all q which is either less than 0 or which is greater than dimension of K. We now observe that the following are certain distinguished members of Q dimensional chain group CQK plus corresponding to each positively oriented sigma q belonging to K. Now, we define those distinguished members as sigma q bar. It is defined on any q simplex tau q as plus 1 whenever that tau q is equal to sigma q. It takes the value minus 1 when tau q is minus sigma q, and it takes the value 0 if tau q has no relationship with sigma q or minus sigma q. These special members are known as elementary Q chains. So, elementary Q chains are particular Q chains as described above. The following theorem says that to know the chain group CQK, it is enough to know the elementary Q chains. So, we define, or rather we state it formally, that CQK is the direct sum of the cyclic groups generated by those elementary Q chains, where Q is any integer between 0 and dimension of K. Let us prove this theorem. Suppose we take any f from CQK. Since K is a finite simplicial complex, we may list the positively oriented Q simplexes of K as sigma q1, sigma q2, etc. up to sigma qt. Let f sigma qi be the integer ni, where I is from 1 to t. Then definition of Q chain says that f of minus sigma qi is equal to minus of ni. Now, we choose a particular member of CQK. Let us take the elementary Q chains sigma q bar I and take a linear combination ni sigma q I bar, where I varies from 1 to t. Definitely CQK being a group, it contains this element. We claim that this particular element coincides with the one which we have started with, that is f is equal to summation I equal to 1 to t ni sigma q bar I. So, let us establish our claim. For any tau q taken from SQ tilde, there are two possibilities. First of all, tau q is positively oriented. In such case, tau q will coincide with one of the members sigma qj for some j. Therefore, summation ni sigma bar q I equal to 1 to t operating on tau q will give n of j, and that is definitely equal to f of tau q. Secondly, tau q is negatively oriented. In this case, minus tau q will be sigma qj for some j, and therefore, summation ni sigma q bar I equal to 1 to t tau q is equal to minus nj, and that is equal to f of tau q. So, in any case, for every tau q, we get that element summation ni sigma q bar I operating on tau q gives us the same element as f operating on tau q. Hence, f is equal to this particular element. Now, since we have chosen f arbitrarily, it proves our claim. Now, we need to establish the uniqueness of the description of f. If possible, let us take f as described in two ways, that f is equal to summation ni sigma q bar I, and that is again equal to mi sigma q bar I equal to 1 to t. Now, taking two expressions on one side, we get summation I equal to 1 to t ni minus mi of sigma q bar I is equal to 0. In particular, for each I equal to 1 to t, this particular element operating on sigma qi is equal to 0, which implies that ni minus mi is equal to 0. So, ni is equal to mi for all I equal to 1 to t. Now, we state a few things as a remark, that CQK is a direct sum of infinite cyclic groups generated by the elementary Q chains. Since up to isomorphism, there is only one infinite cyclic group Z, Qth chain group is a direct sum of as many copies of Z as the number of positively oriented Q simplexes in K. Another point to be noted, that there is a 1-1 correspondence between sigma q, the Q simplexes in K, with the elementary Q chains sigma q bar in CQK. So, with the help of this 1-1 correspondence, we can say that CQK is isomorphic to the direct sum of the infinite cyclic groups generated by sigma q, thereby visualizing the elements of CQK as a Z linear combination of positively oriented Q simplexes. So, in the rest of our discussion, we consider CQK as direct sum of Z sigma q, that is direct sum of the infinite cyclic groups generated by the Q simplexes sigma q instead of the elementary Q chains. For each dimension Q, we have associated an abelian group CQK with the simplicial complex K. Now, it is time to define a rule which will take the elements of CQK to the elements of CQ minus 1K. That means, we are going to define a function from CQK to CQ minus 1K and expect that function to be a homomorphism. Now, we formally define boundary homomorphism. To define boundary homomorphism, we need to define a boundary map from CQK to CQ minus 1K. We call del Q a Qth boundary map from CQK to CQ minus 1K if we define it as follows. First of all, we define this map on the generators of CQK, and then as we know that if we can extend it by linearity on the whole of CQK, then we will get the whole description of the map del Q. Now, if sigma q is any generator of CQK, then del Q sigma q is defined as summation incidence number of sigma q minus 1 I with sigma q minus 1 I. Now, what do I mean by incidence number of sigma q minus 1 I on sigma q? As we have already defined earlier, it can have 3 values, 0, +1 or -1. If sigma q minus 1 I is not a face of sigma q, then this incidence number is 0. If sigma q minus 1 I is a face of sigma q and sigma q has the extra vertex v over all the vertices of sigma q minus 1 I, then adjoining that extra vertex in front of the vertices of sigma q minus 1 I, if we get positively oriented sigma q, then the incidence number is +1, otherwise it is -1. So, this summation is actually a linear combination of the simplexes sigma q minus 1 I, where this summation is taken over all positively oriented q minus 1 faces of sigma q. And as we have already mentioned, that we extend this definition to the entire chain group by linearity and get the full description of del Q. It is easy to see that this del Q as defined here is a homomorphism, and so these are called boundary homomorphisms. Now, if we take Q to be less than 0 or Q greater than dimension of K, then del Q are all taken as trivial homomorphisms. So far, we have constructed a doubly infinite sequence of chain groups and boundary homomorphisms, which we call chain complex of K, and it can be described in this diagram. If we look at any portion of this diagram, then we see that we have successive chain groups CQ plus 1K, CQK, CQ minus 1K and so on, and they are related by certain maps in between. A pivotal result on composition of these boundary maps is given in this theorem, that in this diagram, if we see that if we take del Q compose del Q plus 1, then this composite map has its domain as CQ plus 1K and ends up at CQ minus 1K. We shall show that this composition del Q compose del Q plus 1 is equal to 0 for each Q. Now, let us prove this theorem. It is enough to show that del Q compose del Q plus 1 of sigma Q plus 1 is equal to 0 for each generator sigma Q plus 1 of CQ plus 1K. For that, we start with del Q compose del Q plus 1 operating on sigma Q plus 1. This is equal to, by definition of composite of maps, it is del q on, we apply the definition of del q plus 1 of sigma q plus 1, that is summation of incidence number sigma q plus 1 sigma q I multiplied with sigma q I, and the summation is taken over sigma q I varying over k. Once again, since these are all scalars, the incidence numbers are scalars and del q is a boundary homomorphism, by applying the property of homomorphism, we have summation incidence number sigma q plus 1 sigma q I del q of sigma q I, where sigma q I varies over k. That means summation incidence number sigma q plus 1 sigma I q summation sigma q I sigma q minus 1 j of sigma q minus 1 j, that is equal to summation incidence number sigma q plus 1 sigma q I multiplied by sigma q I sigma q minus 1 j sigma q minus 1 j. But whatever written inside the brackets will have the value 0, as we have already proved in our previous module. So, ultimately the whole thing reduces to 0. So, we define q cycles and q boundaries now. That suppose K is an oriented simplicial complex, a q chain ZQ is called a q cycle if ZQ belongs to kernel of delta q. Now, by kernel of delta q we mean, as usual, all the members of CQ which are mapped to the 0 element of CQ minus 1 k. Now, a q chain BQ is called a q boundary if BQ belongs to the image set of delta q plus 1. As CQK is an abelian group, ZQK and BQK both are normal subgroups of CQK. The first one, ZQK, is called the group of q cycles, and the subgroup BQK is called the group of q boundaries. We shall establish that for every dimension q, BQK is a subset of ZQK, because if you take a member from BQK, call it BQ, then BQK is the image of that delta. So, that means there exists some AQ plus 1 in CQ plus 1 k such that BQ is del q plus 1 of AQ plus 1. Now, taking del q, we get del q on BQ is equal to del q of del q plus 1 of AQ plus 1, but that is equal to del q compose del q plus 1 of AQ plus 1. We have already shown that del q compose del q plus 1 is the 0 map, and therefore, the value of this is equal to 0. So, that means whenever BQ is taken from BQK, it is in ZQK. So, with the help of the last theorem, we now define what is Qth simplicial homology group of a simplicial complex K. Now, suppose we are given an oriented simplicial complex K, and we start with a chain complex associated with that oriented simplicial complex K. Now, if we look at CQK, the boundary homomorphism del Q and the boundary homomorphism del Q plus 1, then inside CQK we see two groups, one is ZQK and the other one is BQK. Now, as we have already proved in the last theorem that BQK is contained in ZQK, and we also know that CQK is an abelian group, all these subgroups are normal. So, we can think of the quotient group ZQK by BQK. So, we define HQK as the quotient group ZQK by BQK when Q is any integer between 0 and dimension of K. But if you take Q to be less than 0 or greater than dimension of K, then by definition HQK is the trivial group 0. Now, we recall certain facts that a topological space X is triangulable if there exists some simplicial complex K such that X is homeomorphic to the geometric carrier of X. That is, X is homeomorphic to mod K. It can be shown that if K1 and K2 are two triangulations of X, then HQK1 is isomorphic to HQK2 for each Q as groups. In view of this, we define qth homology group of a space X as the following. If K is a triangulation of X, then HQX is defined to be equal to HQK for all Q. Let us take an example. Suppose we take a sphere S2 in R3. Then we know that a triangulation of S2 is a tetrahedron. So, let us take the simplicial complex K consisting of all the faces of a tetrahedron. We can compute the simplicial homology groups of K, and we can say that the simplicial homology group of S2 is actually equal to the simplicial homology groups of that K. We can find out by simple computation that the simplicial homology groups of K are the infinite cyclic group Z when Q has the value 0 or 2, otherwise it is trivial.